Okay, so let us start. Okay. Last time, I talked to you briefly about the possibility of taking a prime field, okay, which is just FP or Z or ZP, okay, ZP with the plus and the multiplication modulo P, it's a field, okay, but we can extend it by looking at the ring of polynomials and dividing it by some irreducible polynomial. And this gives us a way to create a field which is not arithmetic. I mean, it's not the usual number theory, so it's stronger in the cryptography view. Okay, so I want to show you today how can we embed this group. I mean, if we, what is the field? I mean, if it's a ring that if you remove the zero, you get a multiplicative group, even a cyclic one. So I want to show you instead of I mean, talking with some element of the extended field, which is a polynomial, I want to show you how to embed this group in a matrix, actually in GLN. So instead of doing the operator overloading, you just take the representation of the elements in this matrix group and do just a usual matrix multiplication. And then you can do in this matrix multiplication all you want to do. I mean finding the multiplication of two elements in the group, finding the order, finding a generator of the cyclic group, and etc. I mean, all the cryptography things we want to do, okay? So I'm going to show you this. After that, we're going to pass through over the project, okay? It's not the final. I mean, we may meet in Tomer some do some changes, but this is the basis thing, the basic thing. I think it's interesting. I mean, if you don't like it, I mean, we can change it. But, I think it gives you, by programming, the understanding of algebra, and of course the use of cryptography. Okay. So you may do it, you're free together, and next time we meet, it's for you to present your work, and we may ask some questions and etc. Okay. So next week we don't meet. We're gonna meet at the presentation. Okay.
I have two questions.
Yes.
One, I guess I will see, but how is what you're going to show us, the matrix representation is different than what we saw last week? Because we saw, I'm not mistaken, right? We saw something like that last week, right?
It's actually it's not different. Okay. I just want to show you why is the operation is preserved. I mean, why is it's what we call the homomorphism. I mean, okay, I show you how to do it, but why is it true? And the next thing I want to show you is in more general. I want to take a case in which the extension is three-dimensional. Okay, and to show you how we create these matrices, but it's true that what I showed you it's the same thing actually, and we have to also to remember I mean two things. One, that the representation of this group depends on the choice of the basis. So now I'm going to show you what is the canonical choice of a base. okay? Because if you take 1 and I, okay, this is not the general case. I mean, we can just take the powers of X, because you have to program it, okay, not to treat a specific case. And something else I want to tell you, of course, that though this group is embedded in GLN, it's a abelian group, because of course the multiplicative proof of a field is an abelian one. So actually we see how this GLN is very rich. I mean, it contains all possible extensions, and I mean, every finite group is actually embedded in GLN. Okay, so once you are able to embed your group in GLN, and you do how to multiply matrices, so it's okay. I mean, you don't have to use operator overloading and etc. Okay, so then, yeah.
Just one, we finished the discussion about the elliptical curves, right?
Yes.
Okay, cool.
Okay. I mean, last year the project was on this, on elliptic curves. I want this year to do it something different.
Yeah, thanks.
Okay, so just a minute. Okay. Okay, so given a prime number, now I suppose that Tomer will give you the prime and also will give you the irreducible polynomial that creates the extension. Given a prime number P and okay, let us let K will be the prime field. Okay, it contains P elements, and if you remove the 0, you get a cyclic multiplicative group. Okay. And given an irreducible polynomial fx defined over k, means that the coefficients here are from k. Okay. Since it is separable, it contains I forgot to say, defined over K of degree N. Okay. Okay. Since it is separable it contains n distinct roots. Okay. Let L be the extended field. I mean, we take our K, we take the ring of one variable polynomial and we divide it by the ideal. I know that Tomer told you about the ideal. It's just what is generated by this polynomial. Okay, so this is actually the zero. Okay, I mean, so what do we get? We get a field that contains this is the free coefficients. This actually cover K, but now we have more. Okay, so this is actually a vector space, but it's more than a vector space. It's a field. Okay, this is a field. Okay, so this field, this new field, contains P in the power of n elements, because each coefficient here has P possibilities. Okay. Now, each element in L can be described as a vector in Kn, isn't it? You just take the coefficients. Okay. And each element in L star is L without the vector 0. Okay, if you write it usually in L, so don't have to write vector, it's just the 0. But if you write it in this description, so it's the 0 vector. Okay, so each element, okay, gives rise to an automorphism of L. Okay, let's write it like this. Suppose we have this is a L star. Okay, suppose we have an element X here. Okay, so how does this gives rise to automorphism? Okay, means homomorphism, and even it is an isomorphism. Okay, that it's from one group to the same group. This is called automorphism. Okay, this is Okay, so what is this automorphism? Just multiplication by, maybe it's not intelligent to call it X because we have already X. So maybe we call it what? We call it Y. Okay, so what is the automorphism? HY. Okay, it's a automorphism from L to L. How HY of some element, how we may call it, sigma, it's just Y sigma. Okay, so once you multiply, I mean, what is the element sigma? Is such an element here. Okay, so once you multiply your element in another element from here, you get another element from here. I mean, it doesn't exceed to n plus 1 because n plus 1 it is described by the lower power here. Okay, we're going to see an example. So actually we get the homomorphism from, let's call it phi, from L star. Remember that any element here gives rise to automorphism. Which is GLN, which is isomorphic to GLN over K, because any element here can be described as a vector in Kn. So what are the linear transformation from Kn to Kn are matrices, okay? Which are invertible, of course. Are the elements but the image of phi, of course, it is far from being subjective. Okay, because this is an abelian group, and this is far from being an abelian group. I mean, it's just a little subgroup inside here. Okay. Okay, so I wrote to myself, let us okay, I wrote here some example, just a minute, and I would like you to do the same in your project. Okay. Example. Let L be F3. F3 contains just 0, 1, 2, 0, 1, 2, 3 elements. Okay, so it's easy to verify that this polynomial is irreducible. Just to substitute the element of F3. I mean, 0 does not give us 0. 1 is still 1, and 2, okay, is 2 minus 2 is 0. It's 1. I mean, you don't have a root here that comes from here. Okay, so this is an irreducible polynomial over F3. But instead of now searching the roots of this polynomial, I suggest the following. I mean, we have many choices of bases of this field. I mean, we just need 3 elements in the basis in order to span this L. What is this L? This L is A0 plus A1 x plus A2 x squared, okay? Such that, of course, AI belongs to F3, and x square, no, x3, sorry. Why didn't I write it here x3? Because x3, it's actually x minus 1. Okay? Because this is 0. You have to understand what is this description. These are shifts of this ideal, shifts of this subgroup. So once you get to an element in this subgroup, is just the 0. Okay, so if this is the 0, okay, so x3 is just x minus 1. Is it clear?
In the project,
sorry?
Yes, in the project we'll get the field and the irreducible
yes
field?
Yes, I mean,
okay.
I mean, you have, I mean, Tomer is an expert on these things. He has library functions that provides for any field, for any dimension. Okay, so he will provide you. Okay, so now we want to find it calls a matrix realization of L elements or L star. So how do we do that? So we say that any element here, I mean, first, what is a L star? I mean, how many elements we have here? We have 3 in the power of 3 minus 1. I mean, we have 26 elements here. Why minus 1? Because we have removed the 0. So we have 26 elements here. Okay, and this group is cyclic. So you have a mission to find a generator, but we are going to see what is the generator here. Of course, the generator here is a polynomial, okay, of course. Okay, so the basis that we are going to choose is always the powers of x. That's all. Is the simplest case, okay? I mean, this L is span over F3 by 1x and x squared. This is what is written here. I mean, this all the possibilities to take A0 times this plus A1 plus this. That's the span. But of course, we know, I mean, this thing. Okay, we don't have to write it. So this is the basis. So we only need to understand what is the action of the basis element on the general element. I mean, remember that is this automorphism of L, to translate it into matrix, and then it's an homomorphism. I mean, it preserves the operation of L star. Okay, so and I recall that L is isomorphic to, if this is K, okay, so K in the power of 3, because it's a three-dimensional extension. You see, we have 3 elements. Okay, so of course 1 doesn't do anything. When I write star, I mean the action. Okay, I mean what is transmitted to what. So 1, when you see, now I'm going to write the elements of L using the description in K3. Okay, so how does one transmit A0, A1, and A2? It doesn't do anything.
Can I ask a question about the writing?
Yes.
Let us see there. Can you please?
The action. The action.
Okay, thanks.
I'm sorry. I mean, we didn't talk enough. I mean, we didn't talk about what is an action, but in this context, it's just the transmission of elements in K3 to K3. Okay, but there is a notion of an algebraic notion of an action, and the action is linear. Okay, I'm going to tell you something about it. Okay, so now I saw what one did. Now what X does. Remember that this vector represents this polynomial. So when you multiply it by X, it becomes A0X. I mean, this does just increase the power. But now, instead of writing X in the power of 3, I'm going to write this. So this is the height of the extension. So it transmits a vector A0, A1, A2 to what? To minus A2. This is the free coefficient, to A0 plus A2 and to A1. Is it clear?
Yeah.
So what is the matrix? I mean, here the matrix under phi was very simple. It was just I. But what here, the matrix is here. So, okay, so let us think of it. So it is okay. So if I call this is actually phi of x. This is the matrix. And the same you do for x squared, okay? Now, since the action is linear, what do I mean? I mean that the action of some combination of this basic element, I mean a plus a1x, it's just okay. So now we get that our L star is isomorphic to phi of L star, because it is we call it a faithful representation. I mean, every element, I mean, it's a monomorphism, okay, and it lies inside. I mean, it's a subgroup of GL3 over F3. Now, of course, this is much greater than this. This contains only 26 elements. And this much more, much more. This is an abelian group. This is not an abelian group, but it lies inside it. Okay, for example, this element phi(x), okay, let me try to show you. Okay, just a minute. Sure. Okay. You see now the symbol of? You see now the symbol of?
Yeah.
Okay, so before the lecture, I tried to figure out the order of this matrix. Okay. Now I know, due to Lagrange, that if the group, and this is something that we have to take under consideration. I mean, when you find, and when you are looking for the order of an element, you only have to take under consideration the possible powers that can be the order. If here, for example, the order of the whole group is 26, then it can be only 2 and 13. Okay? So I took here the power of 13 of this element. And what did I get? Now, remember that the characteristic of the field didn't change because of the extension. It remains free. I mean, everything is modulo free, is 0. So what is this matrix? This is the power 13 of this representation. What is this matrix? You know what is this matrix? You don't know? It's minus I. Because everything vanishes here. I mean, every multiplication by 3 vanishes. And this is minus 1, minus 1, minus 1. Okay? So what is the, I mean, why didn't I show you 26? Because the symbol app didn't want to show me. I mean, he told me it's a too large power. But if I know this, I know 26 because we are over F3. 26 is 1, is the identity. So this is this matrix, or the origin of this matrix is, say, X. X is a generator of our group, which means that any element, any polynomial, even the coefficients, I mean, the free coefficients can be described by some power of X. Okay, so the order of our X is 26 because this is minus 1. Minus 1 in the power of 2 is 1. So this is a generator of our group. Okay. Okay. So, are there any question until now? So we have seen how to embed the multiplicative group of an extension of a prime field inside the matrix that is considered as the group of automorphism of the vector field. Okay, so what is the advantage of going to matrices? I assume that you have in any language of programming some function in the library that implements, matrices multiplication. Okay, so you don't have to really do some operator overloading. You have just to find, to tell the computer, okay, given an element of L star, and for me, I mean, you will have to create here some interface, and there doesn't have to be a GUI, but some interface that asks the user to give him some vector in the power in the length of the extension dimension. Okay, so it does represent some element in L star. Okay, and you will have to, I mean, in the program, to go to the suitable matrix and do all the operation of the group in terms of the matrices in this subgroup. Okay, so let us read that together, the project. I mean, it may not be final because we may change some things, but this is the idea, okay? But by the way, do you have a question until now? Okay. Given a prime P, let K be the corresponding prime field and let L be an n-dimensional expansion of K by an irreducible polynomial defined over K of degree n. Okay. Write a code in some language that supports object-oriented. I think it's the best, and do it in this way. It can be C, I mean C++ or Java or Python, I don't know what you want, which implements a K matrix realization of the elements in the multiplicative group L star, which means an embedding of this group inside GLNK. And write G for the image of L star inside GLNK. As I told you, it's a much smaller group than GLNK. It's an abelian group. Okay, by the way, I didn't, just a minute. I didn't wrote you something important. Okay, this obtain map from L star to GLN is a homomorphism. Because if you take two elements in L star, so phi of xy, okay, will be actually the automorphism that multiplies by these two matrices, okay, will be actually the automorphism xy, okay, which do what? Given an element L, say don't L, sigma, it does x, it multiply xy by sigma, okay, which is exactly taking hx okay. So this show you that this is because what is a matrices multiplication? It just gives rise to the composition of, I mean any matrix represents some linear transformation, and when we multiply the matrices, this represents the composition of the two transformations. Okay, so this is an homomorphism of groups. Okay, so it preserves the operation. Okay, so let us say Okay. So write the code. Okay, A1, we see them. 2. Okay, write a function that given 2 elements A and B in L star. Now this AB will be described by the user in terms of vectors in Kn. I mean, you will need to write K entries, N entries from K. So it will be given the K. I mean, what is the prime? And inside each entry, you will have to write some coefficient from 0 to p minus 1, n times, okay? So it gives you A and B, and in return, it gets the vector AB. Now, how do you do it? Using phi. I mean, you are going to the matrices. You see what is the multiplication, and give you back. Okay. Now you have to write a function that given an element in L star. Again, I mean, now it's described as a vector over K. You return its order. Now here, I mean, you may not do the thing in the most trivial way. As I told you, there are possible natural numbers that can be candidates to be the order by Lagrange theorem. Okay, so maybe you have some, you can be some, I mean, efficiency here. I don't know. 4, write a function that finds a generator. Now, this is maybe the most difficult thing here. I suggest you the following. Let us first find a generator of K star. How do we find a generator of K star? Of course, we can try all elements, but if K star is big, this will be a little hard. What you can do, okay, and this you can use free. I mean, you are doing some table. Inside, you write every time the order of the elements that you have checked. And once you see 2 elements with co-prime orders, of course, here everything is abelian. So we have learned that the order of the multiplication of these elements with co-prime orders is the multiplication of the orders. You see what I mean? You want me to write it, or you understand what I mean?
Please write it.
To write it?
Yeah.
Yeah, okay. If X, Y in L star have OX and OY is 1, then the order of XY, and now we use the previous task to find XY. So you have to use also the how find order and how to find xy. So the order of xy will be the multiplication of the orders. So this is a way to grow up. I mean, to find a larger order until you find, for example, in the last example that we have seen, 26, it was sufficient to find an element of order 13, an element of order 2. That's all. The multiplication of the elements will be of order 26. Okay, it's, I mean, a generator of the group. Okay, so you have to put it in a table and maybe, okay. By the way, I'm not sure about the implementation. I mean, you are researchers. I mean, maybe you have some idea. I'm sure you can have better idea. I mean, you don't have to put much time on it, okay? But if you have some idea, it will be, I think, interesting, because these things are, I mean, can be very implicative. Okay.
So you said this was the first step, because the finding directly generator of L star is difficult. What is the following step?
So you find the generator of K, okay, and Tomer will explain you how to go from the generator of K. This is called the Hensel lemma, okay? He will explain you how to move from K star to L star, okay? This is very interesting, I think. Okay. So I leave it to him. 5. Using the baby step, giant step, you have to create some hashing table to go in steps of the square of p in the power of n minus 1. Okay, this is the giant steps. So you have to put, as we have seen, the results in some hashing table, and then go in a smaller resolution, in a thinner resolution, and find to compare each time the giant step with the current baby step. And once you get a true, you find actually x. Okay. Now these are not numbers; these are polynomials. So you have to think how you put these polynomials in a table. Okay, by some criterion of hashing function. So you have to find this x, this power, and I think that once you have finished with this, you will be in a better situation to understand, I hope, cryptography and how to improve, because the cryptography today is not with the extensions of field, etc. It's just arithmetic, and against this arithmetic you have the usual attacks of the number sieve and etc. So maybe you will find somewhere in industry a way to improve, because we more and more use the internet, and we must find better way to do a cryptography in a stronger way. I heard, for example, that in China, which is very developed in these things, I mean, even one in the street that demands some money, I mean, maybe a poor man, I mean, he gives you his cellular, because everything is with the Alipay, So we are going towards this direction. I mean, everything will be not money, but electronic money. Okay, so I think this is first interesting, and secondly, maybe very implicative. Okay, so if you don't have any question, we may stop now. Okay, and we will fix an appointment. Of course, you are more than invited to ask me question. You know my WhatsApp, my mail. Now it's your turn. I mean, do you have any comments? Do you think this? I mean, do you think something else, or?
What is the timeline of the project?
Sorry.
What is the timeline? How much time will it be given?
Tell
When?
me what do you want?
Uh,
I mean, I'm not restricted.
I'm fine with whatever.
Okay, maybe you want to ask the other privately. I don't know.
I think if we have the option, so maybe we'll just start doing it, and then we'll get some notion of how
Okay,
much time it will take.
okay,
And I think maybe in a week we can tell you what we think, and then you can tell us okay or not. We think
Okay.
of something reasonable.
okay. Now, Tomer will give you more details, but I want some explanations. I mean, not just code. If you can write some words in English explaining what you do. Okay, so I can read it because we are going to read it before our meeting and see it works. Okay, and so you may write some. You will have to submit a code together with some documents. Okay.
So we have to made it separately, or we are just
No, together,
Yeah,
but
like commenting the code.
yes, but in
like
the
that.
presentation, we may ask each one another question.
Okay.
And the question will be on the
Yes, on the work.
itself, or from all over the course we need to
No.
memorize everything.
No. It will be around the project.
Okay.
Okay. I mean, the course will just give you the tools. So it's okay.
Yes.
You think it is interesting?
Yeah, it seems interesting. It's hard to quantify in advance how much time will it take, and
Yeah.
Yeah.
but yeah, I guess it's something we need to.
So maybe
Discuss
you can divide your work among you. I mean, not only one will do everything, of course.
Yes, of course.
But the final submission is one. I mean, one code, one document.
Okay.
And it will be frontal at the university, or it will be in a Zoom session?
No, in a Zoom session.
Okay. And it will be all of us together, and
Yes,
every
together
one of us
with
will be
Tomer.
listening.
Together with Tomer, me and Tomer and your three of us, or of you.
Okay.
Okay? So for now, thank you very much. I hope you enjoyed. I enjoyed anyway. And I hope that it will give you something in the future. I don't know. Okay.
Yeah. So, yeah.
Okay, I have one question. Up to like what time we can extend the deadline, because I also have 2 more exams to write.
So talk to your friends. I mean, I'm flexible.
Okay, so we three of decide
Yes.
what is suitable. Okay.
Okay. So thank you very much. and have
Thank
a
you.
pleasant work.
Thank
And,
you. Can I talk with you for a minute? After,
sorry?
Can I talk with you for a minute after the session ends?
Of course, I'm here.
So.
Bye.